So, last time we looked at the fact that because ring of integers in a number field is a Dedekind domain, we can take any ideal in it, a non-zero ideal, and get a prime factorization of it. In particular, if you have extensions of number field L over K, then you can take a prime ideal of K and extend it to an ideal in OL. It need not be a prime ideal there, we look at its prime factorization and we attach important invariants to it like ramification index, residue degree, etc. And I stated a lemma which said that the extension, the degree of the extensions is related to these ramification indices, residue degrees and the number of primes in a particular way. We proved that lemma when the base field was Q. We will postpone the proof of the general result to a later point. So, we will not prove that today for a general extension of number fields. But we will look at, we will define another important invariant of a number field which is called the ideal class group, and we will prove that ideal class group of a ring of integers of a number field is a finite group, finite abelian group. Okay. So, that is our aim for today. We can define the ideal class group for any Dedekind domain. Okay. So, let us do that. So, let R be a Dedekind domain. Okay. Let J sub R be the group of non-zero fractional ideals of R. Okay. Now, inside this there are non-zero principal fractional ideals. So, here is a definition: a fractional ideal A of R is called a principal fractional ideal if A is x times R for some x in K. Okay. So, in particular if A is a non-zero principal fractional ideal, then x will be non-zero. So, it is exactly what you would do for an ideal. An ideal is called principal if there exists some x in R such that the ideal is x times R. So, instead of an ideal we have a fractional ideal. So, we let our x be an arbitrary element of K, which is the K is the quotient field of R. Okay. All right. So, what do we do next? Let P sub R be the group of principal fractional ideals. Okay. So, amongst all principal non-zero fractional ideals. So, principal non-zero fractional ideals. Okay. All right. So, P R, this is a subgroup of J sub R, and we can define the quotient. So, C, let me define it as CL sub R, this is J sub R modulo P sub R, this is called the ideal class group of R. Okay. So, this is the definition of ideal class group. Okay. Innocuous looking, of course, but So, here is a lemma that I am not going to prove because it is very easy. There is an exact sequence like this, which is 1 going to units of this, going to the principal non-zero principal fractional ideals of R, going to J R, going to C L sub R. Okay. Well, okay, I said I am not going to prove this, but by definition, so let me just say by definition there is a, sorry, this should not be PR, this should not be PR, this should be K cross. By definition there is an exact sequence 1 going to PR, going to JR, going to CLR, right. But any principal fractional ideal is generated by a non-zero principal fractional ideal is generated by a non-zero element of K. So, there is a sequence, there is an exact sequence 1. So, any non-zero element of K gives you a principal fractional ideal and vice versa. But this map is not injective, the map from K cross to PR is not injective. Two different elements of K cross could give you the same principal fractional ideal. And when do they give same principal fractional ideal? Precisely when they differ by an element in R cross. And so, you just put these two exact sequences together to get your lemma. Okay. If you are not comfortable with exact sequences, I suggest that you get comfortable with exact sequences and start using them, exact sequences, commutative diagrams, diagrams of field extensions, because that is going to help you a lot in thinking about problems in algebraic number theory, arithmetic geometry, algebraic geometry, etc. So, you should try to think in terms of exact sequences. Okay. So, here is an example, the simplest of examples is that if you take R to be Z, then K is of course Q, right, and any non-zero fractional ideal is principal. Hence, the class group of Z, which we will soon start denoting as class group of Q, is trivial. Okay. All right. So, I am going to prove a few algebraic results first before we go on to the proof of finiteness of the class group. So, here is the first result. Okay. It says the following. So, here is a proposition. Let R be a Dedekind domain, then R is a PID if and only if R is a UFD, a unique factorization domain. Okay. So, in general a PID is a UFD, but the converse is not true. Okay. So, let me remark for a ring PID implies UFD, but the converse is not true in general, right. As an example, you can look at R to be ZX. So, this is a UFD, but it is not a PID. Okay. What the proposition is saying is that for a Dedekind domain, being a PID is same as being a UFD. So, I am not going to prove that PID implies UFD, because that portion is true more generally, and you may have seen in an algebra course. So, I am not going to prove PID implies UFD. So, we prove so let R be a Dedekind domain and a UFD. Okay. We want to show that R is a PID. So, every ideal in R is actually a principal ideal. So, because you have factorization of non-zero ideals into prime ideals in a Dedekind domain using factorization of non-zero ideals into prime ideals, it is enough to prove that any prime ideal is principal, right. Okay. So, we just need to prove that any prime ideal in a Dedekind domain which is a UFD is actually principal. So, we have already here used that it is a Dedekind domain. So, we better use somewhere that it is a UFD. Okay. So, let P be a non-zero prime ideal in R. So, what I do is I take alpha in P. Now, I use that we have a UFD. So, alpha is equal to alpha 1 so on up to alpha s, where alpha i's are irreducible elements. Okay. So, what we have is alpha 1 times alpha s is in P, right, which means that there exists I such that alpha I is in P, okay, which means that alpha I is contained in P, but this is a non-zero prime ideal. And hence maximal, because R is a Dedekind domain. Therefore, P is equal to alpha I, and we are done. Okay. So, for a Dedekind domain, being a principal ideal domain is same as being a unique factorization domain. Okay. Now, a corollary of this is the following: let R be a Dedekind domain, then R is a unique factorization domain if and only if its class group is trivial. Okay. So, right. So, class group is trivial if and only if R is a PID, right. Every fractional ideal is principal, every non-zero fractional ideal, so which means every fractional ideal is principal in particular. So, what does it mean for ideal class group to be trivial? It means that every fractional ideal is a principal fractional ideal. So, in particular all ideals are principal ideals, right. And so, being UFD is same as every ideal being principal, every ideal being principal is same as every fractional ideal is principal, and every fractional ideal is principal is same as ideal class group is trivial. Okay. So, ideal class group measures how far your Dedekind domain is from being a PID or a UFD. Okay. So, the abelian group CLR measures failure or what is also called obstruction for R to be a PID which is same as being a UFD. Okay. So, that is why ideal class group is such an important object. So, if the ideal class group is trivial, it means there is no obstruction for any ideal to be principal. Okay. All right. So, now this was about general Dedekind domains. Now, let us get back to our special Dedekind domain which is the ring of integers. So, let K be a number field. We denote CLK to be CL of OK. So, that is our definition of CLK, right. We will not talk about ideal class groups of other subrings of K. We can talk about ideal class groups of other subrings of K which are not rings of integers, but we are not going to do that, and so it makes sense to just say ideal class group of K is this. Okay. So, example CLQ is trivial, right, and CLQI is trivial, right. I is square root of fixed square root of minus 1, right, because we know that OQI is just ZI is a PID. Right. We know this because in fact ZI is a Euclidean domain. So, in particular it is a PID. Any Euclidean domain is also a principal ideal domain, and because it is a principal ideal domain, its ideal class group is trivial. Okay. Now, here is a theorem. So, this will take us some time to prove. We will get started today. So, let K be a number field, then CLK is finite, is a finite abelian group. Okay. So, this means that although unique factorization does fail in rings of integers of arbitrary number field, it does not fail so badly. It is measured by a finite abelian group. Okay. So, so it does not fail very miserably. Let me also remark that ideal class groups of general Dedekind domains can be infinite. Okay. This is very specific to number fields, that when you take the ring of integer of a number field, its ideal class group is a finite abelian group. In general, for Dedekind domains, the ideal class group need not be finite, and we are going to use norm in a very crucial way to prove the finiteness result, and this norm is not necessarily available in other situations, which is why we do not necessarily get a finite group. Okay. So, as I said, this will take some time. So, let us start preparing for it. So, okay. So, the first, let us prove first a lemma. Let x be a real number x greater than 0, then there are only finitely many integral ideals, I am emphasizing the word integral, A in OK such that norm of A is less than or equal to x. So, if you go up to any x, norm of that there are only finitely many ideals which are of norm less than or equal to x. Okay. This is a crucial ingredient that will go into this. This is a simple lemma, but it is also a crucial ingredient that will go into proof of the theorem. So, the proof of this is very easy. If norm of A is equal to n, okay, I am using n for degree of k over q. So, let us say if it is m, okay, then this means that index of A in this is m, right. That is the definition of what a norm is. It is the index of A in OK, right. And so, what I can do is I can look at the so let m be such that m to the power n okay. Is greater than x. So, I can always for any m bigger than 1 I can always find sorry, yeah. So, no, I mean for any my n is given to me, right. So, recall that n is equal to degree of k over q. So, my n is fixed. So, I can always find some m large enough such that this holds and I fix such an m. Then m times OK has norm, so norm of this ideal is m to the power n, right, which is greater than x. And now I consider OK modulo m times OK, right. This thing is isomorphic to z mod mz to the power n as additive groups. Right. And so, there are only finitely many subgroups. So, there are only finitely many subgroups of OK. So, finitely many subgroups, let us say G of OK such that M OK is contained in G is contained in OK. So, there are only finitely many additive subgroups like that, right. Now, if norm of A is less than or equal to x, then yeah, okay, I should have, all right. So, this is not quite then the right thing, okay. So, then okay, fine, sorry, let me just take, let me forget about the n here. and just write it like this. Okay. All right, everything is still true. So then what it means is that m factorial times OK is contained in A is contained in OK. So, hence there are only finitely many ideals with norm less than or equal to x. All right. So, yeah, this is a simple lemma, but it's going to be crucial here. Okay. All right. So, going to the proof of the theorem, what we are going to prove. So, let me write it as a remark. To prove that CLK is finite, it is enough to prove that any ideal class, and so I'll spend a few minutes explaining what an ideal class is. Any ideal class contains an integral ideal of a bounded norm. So, that is going to be our strategy. Let me explain the terms that go into this remark. So, recall the definition of what an ideal class group is. So, CL of K, this is J sub OK modulo P sub OK, right. So, you can think of CLK as equivalence classes of fractional ideals, equivalence classes of non-zero fractional ideals Okay, so A is equivalent to B if there exists X in K cross such that A is equal to X times B. Okay. So, you can think of, so you can verify, take this as a simple exercise that CLK is just J sub OK modulo this equivalence relation. Okay. This is precisely what it means to differ by a principal fractional ideal. Okay. So, ideal class is this equivalence class. So, ideal class is an equivalence class of non-zero fractional ideals. Right. And if you see that any so this, I mean, all I am saying, whatever I am saying now is true for a general Dedekind domain, although I am writing it only for number fields. So, so here is a lemma, any equivalence class contains an integral ideal. Right. It is not necessary, I mean, a priori there is no guarantee that an equivalence class will contain an integral ideal. It contains a fractional ideal, but why should that fractional ideal be integral? So, here is a proof let, so I will denote the equivalence classes by square bracket around them J sub OK modulo this equivalence relation be an equivalence class of A, right. And so, A is a fractional ideal. So, I can write it as P1 dot 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 up to PR Q1 up dot 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 up to Qs for some prime ideals, right. Now, I can take X to be any element of Q1 up to Qs, but not 0, right. Then X by Q1 up to Qs, this is an integral ideal, right, because if you take prime factorization of X, all these Qi's will appear in that prime factorization. Okay. And so, X times A has the same equivalence class as A, and X times A is the ideal generated by X over Q1 up to Qs, and then P1 up to PR is an integral ideal. Okay, so, every equivalence class of fractional ideals, it actually contains a principal, it actually contains an integral fractional ideal, but we are going to show next time that in the case of number fields, a equivalence class of fractional ideals, it contains a integral ideal of bounded norm. Okay. So, the bound will only be in terms of the number field, not in terms of the equivalence class. So, this will then, along with our lemma that there are only finitely many ideals of bounded norms, will tell you that there are only finitely many equivalence classes, and hence the ideal class group is finite. Thank you.